Hello everyone, my name is Shuran Yan, and today I am presenting my CS358 final project, TransPIM, a memory-centric approach for accelerating transformer models. This work is based on an HPCA 2022 paper from UC San Diego. The key idea is to improve transformer performance, not by changing the algorithm, but by changing how data moves inside memory. Transformers like GPT or BRT are extremely powerful, but they have a major bottleneck. More than 60% of the total time is spent moving data, not computing. This means the hardware is basically waiting for data to arrive instead of doing useful work. So, improving data movement is the key to speeding up transformers. The main reason for this memory bottleneck is the attention operation. Its complexity is O of L squared, where L is the sequence length. If we double L, the number of attention scores becomes 4 times larger. For a sequence length of 4096, we generate over 16 million attention values. And all of these values need to be loaded, stored, and moved through memory. That's why transformers' performance is dominated by memory traffic. Let's look at how the traditional PIM, in other words, processing in memory systems work. They use what's called layer-based data flow. First of all banks process the FC layer. Secondly, they all banks switch to the attention layer. Then, all banks switch to the FFN layer. The problem is that every time we move from one layer to the next, we reload and reorganize data. This creates a lot of unnecessary data movements, which leads to poor performance. Here is the latency breakdown I reproduced. On the left side, for the traditional method, the red portion, data movement, takes over 62% of the total time. On the right side, for TransPIM, data movement drops to 40%. Just changing the data flow pattern already provides a big improvement. This chart clearly shows that the main bottleneck is not compute, it's memory traffic. TransPIM introduces a simple but powerful idea. Instead of processing by layers, we process by tokens. Each memory bank takes a small group of tokens and processes them through all layers, which is FC, attention, and FFN. And the key benefit is the data stays inside the same memory bank from start to finish. No reloading, no reorganizing, just reuse the data across layers. Okay, so here is a direct comparison. For the layer-based, Bank 0 loads all tokens and runs FC, then reloads the same tokens again for attention, then reloads again for FFN, which means that's lots of wasted movement. Then for the token-based, Bank 0 gets token 0 from 511 and processes FC to attention to FFN in one place. Bank 1 handles tokens 512 to 1023 and so on. The data stays local. You can think of layer-based as an assembly line with constant handoffs. Token-based is like one worker completing the entire task. It's simply more efficient. However, token-based data flow brings a real challenge. Attention requires global information. Each token needs to attend to all other tokens. If different tokens are stored in different banks, then Bank 0 must see K matrices from all other banks. So we still need bank-to-bank communication. The question is how to do it efficiently. TransPIM solves this using ring broadcast. Here's how it works. First of all, each bank first computes local attention using its own K matrix. Then, the K matrices rotate across banks, which is from K0 to Bank 1 to Bank 2 and so on. After a few rounds, every bank has seen every K matrices. The key benefit is that this transfer happens in parallel, thanks to the ring links between banks. This is very similar to the ring collectives we've learned in CS358 for MPI. It avoids bottlenecks and scales efficiently. Now, let's look at the hardware. On top of the PIM units, TransPIM adds, first, ACUs. These handle operations like softmax and reduction, which pure PIM is not good at. Second, ring links. These enable the fast parallel communication I just described. The best part is that this design adds only 4% more chip area, which is well below the typical industry limit. Let's see the demo code. I implemented a simulator to compare layer-based and token-based data flows. The code constructor has 4 main parts. First, layer-based simulation. You can clearly see repeated reloads for every layer. Secondly, token-based simulation. Data is loaded once and processed through all layers. Third, performance calculation. I count data movement and compute operations, then calculate speedups. Last, visualization. I generate latency breakdowns, speedup curves, and layer analysis. Let's see the demo execution flow. The demo runs in 6 steps. First, initialize parameters. Second, simulate layer-based data flow and simulate token-based data flow. Then, compare their performance. The speedup is over 8,000. Then, generate charts. Last, print results. The whole simulation takes less than 3 seconds on a laptop and uses only about 50 MB of memory. So the chart shows the results. As you can see, the speedup grows exponentially with sequence length. This matches the theory. So the attention reduced data movement gives an exponential benefit. Here comes the question. Where does the benefit come from? Most of the benefit comes from the attention layer because it handles L multiply L matrices. Token-based data flow greatly reduces the number of times these large matrices need to be loaded or stored. FC and FFFN also benefit, but attention is the biggest win. All these things so far reminds me what we've learned in the lecture of CS358. The memory hierarchy, the data locality, parallel computing, and Amdahl's law, which identify the bottleneck and optimize it. I would like to summarize the contributions of TransPIM. First, software. Token-based data flow, which is a new way to schedule transformer operations. Second, hardware. Hybrid PIM and MMC architecture with ACUs and ring links. Third, co-design. Software and hardware work together to achieve speedups over GPUs in real paper. Thank you everyone. That is all I want to share today. If you have any questions, please comment here. Thank you.